If you think about this in human terms, right, the way we work with data, it's a mess, right? We are not computers. There's no memory bank. There's no parallel processing. If I try to read every line of Ulysses at once, I probably just get the same thing out of it as I would reading it from beginning to end. If I try to read every line of Shakespeare at once, it's just soup, right? If a computer does that, if you ask it to find the word thou, it can happily read every line of the text at once, because the text as the computer knows it is just a symbol of a set of voltages. So it's just looking for the reoccurrence of a pattern in many places. The goal today is that we spend some time thinking about what a computer really is. As a consequence of that, think a little bit more deeply about what digital stuff really is. And hopefully, having done that, give you some tools and frameworks and smart questions to ask, so that as you encounter digital preservation problems, you have ways to start working towards a solution. And as you inevitably work with all of the other people who surround a digital preservation problem, you have some ways to think about and understand what they're saying to you, and also to translate the things you want to accomplish into terms that they'll understand. I want to spend a little time on the history of computers and computing, right? So I want to make sure that you kind of walk out of today with the computer not being a mysterious box that connects to a screen and tells you things, but understand that it's a device that was made by people to accomplish certain purposes. And in its complexity, it's nearly incomprehensible, but in its basic principles, it's a pretty simple thing. And so, having started us today in the Bronze Age, I'm going to leap all the way ahead to the 19th century and just talk about a couple simple machines, or semi-simple machines, right? So a very simple machine like a lever, right, is pretty easy to understand. It has a little algorithm where, like, you apply force here and the force is multiplied on the other end of it. A more complex machine like a gear train on your bicycle takes force at one end and transfers it to a different set of gears, which have another multiplying effect, right? And they spin a wheel. In the 19th century, we start to have all of this sort of mechanical revolution. And I would argue, and others have argued, that in some ways, by 1801, we have all the basics of a computer up and running. So Joseph Marie Jacquard introduces punched paper cards into looms. They're a template that essentially says, put all of the shuttles in this position and fire the string across the weft. Snowden and I are going to have to double team where she'll supply the vocabulary and all. And you can start to create very intricate patterns if you have enough cards in sequence, right? To just set these positions of the stops of the loom over and over again. This was essentially programmed. It was not reprogrammable, right? You couldn't really, I mean, I guess you could hang around punching random holes in cards, but you could execute the same sequence of steps over and over again. In 1837, an even quirkier fellow, Charles Babbage, designed a fully programmable mechanical computer. And parts of it were actually built in his own lifetime. And the goal was to calculate mathematical tables. So if you grew up in the pre-computer era and you had to do something like find the cosine of a number, there was laborious math involved, or there was looking up close by numbers on a printed table of cosines and interpolating to get a value, right? And inevitably, those tables would have mistakes in them, right? Because the way you got the values was by doing laborious math. Then you handed your manuscript off to a printer, and inevitably some of those printers were working, say, like Friday midnight, and it's pretty easy to switch 7 and 3 as your setting type. The net result of that could be like a ship running into something it was not supposed to run into, right? So there was a real urgency to get better mathematical tables, and hence Babbage's work on trying to automate the process of doing computing, of doing calculation. not long after, in the 1880s, Herman Hollerith started doing experiments with paper tape, with punched cards like Jacquard had used, and experimenting with tabulators, so sorting devices and key punch machines. Hollerith's company was later merged into IBM, and they used punch cards for the United States Census in 1890, which still to this day I find a little upsetting to my notion of how history works, right? That in the late 19th century, a few decades after the American Civil War, prior to the building of most of the infrastructure we live with today, we essentially did the census on computers, right? That the media has changed, but the basic process of encoding data was pretty well established. Boolean algebra, right? The sort of ifs and ands and ors and exclusions that we use to describe search routines or computer operations, the vacuum tube, punch cards and tapes, teleprinters, all developed in the 19th century, right? All of the basic systems that we use for doing computing existed before we ever thought to carve circuits onto silicon dies. I want to show you, just for kicks, what the difference engine looks like. This was built in London by the Science Museum. Took them about 6 years. It weighs a whopping 2.6 tons and has 40,000 separate clanking and interchangeable parts. You cannot call an Uber on it. It doesn't show up well, but you'll get it on the slide. You can go take a look at the whole thing. Here's the whole apparatus, right, in all of its glorious brass work. And you can see it has, it's a complex gear train, and you can feed instructions to it using punched cards. And it actually outputs here to an actual printer. So you can set up a series of calculations, turn the crank, spin, you can see all of the numbered dials here, will shuffle along. They have this really ingenious carrying mechanism where if it clicks over to 0 in this column, it moves a little rod to say, add 1 to the column adjacent to it, and the whole thing clicks through. I saw a demo of it, and the guy was saying that one of his big surprises after they'd got it built was just how strong you had to be to do computing. You're moving, essentially like several hundred gears to, divide 7 by 3, right? The whole thing kind of clicks through. And you get a number at the end of it, right? And that number could represent all sorts of things. You could assign numbers to represent letters if you wanted to print something. You could have numbers represent numbers. You could have numbers represent pictures, right? In fact, there's a wonderful novel by William Gibson and Bruce Sterling called The Difference Engine. It's a work of speculative fiction where they imagine what our world would look like if Babbage, like most people who invent giant clockwork computing devices, was a little bit of an eccentric, never quite got to finishing a unit. So they imagine an entire world built on mechanical rather than electronic computation. It's a good read. The important thing to recognize with all of these things, Jacquard looms and difference engines and Hollerith tabulators, is that they're automating things, right? Machines repeat procedures. Analog machines repeat physical procedures, right? So you turn a crank and it turns gears and predictable things happen. Digital computers repeat logical procedures. Computer hardware is a physical instance of a logical operation. So if you built an OR gate, you would send electricity down it, and depending on the condition stored in the gate electrically, you would light up this branch or you would light up that branch. And if you had an AND gate, you would add those voltages together to produce another result. And if you did that 10,000 times per millisecond for several milliseconds over, you might be able to do something like have Excel substitute the letter T for the letter U, right? Numbers representing letters, right? You display those on the screen using coding that says these numbers represent these pixels being illuminated, right? And you would do this ad nauseum, but you're really just repeating a logical operation. I included a link here, and we're not going to spend a lot of time on this, but I just want to show, if you look at the article on logic gates in Wikipedia, will essentially walk you through all of the different types of logical operations you can create in hardware, right, and different methods for doing that. You could create these things with, as we do now, silicon dies that are printed essentially with a circuit board. You could create them with people with semaphore flags, right? You could create them in brass. And each one of these is just a way of using some physical signal, an electron, a flashing light, the position of a gear, to convey a logical truth value, right? And just like the exercise we did this morning, it's purely an automated process. Once you know that you subtract one or move those things one step down the alphabet, the entire code clicks into place, right? And if you were to greatly magnify the circuits inside your computer, what you would see would be a lot of logic gates, right? To route voltage around so that the voltage represents a number or a letter, right? So there are a couple of things that computers are going to do. One is arithmetic, right? So they're going to add or divide or subtract or manipulate numbers. They're going to do logic, so they're going to put things together, split things apart, or negate things. They can do an operation called a bit shift, right, where you take the entire register of a memory bank, for example, and just move it, right, from one position to another. You can copy from one place to another. You can compare bigger than, smaller than, or equal to. And you can set conditionals, right? Do this thing if that other thing has happened. You can also move computation to a new address. So data can be calculated in one register, right? So it's put in one memory bank and an action has occurred to it, and you can say, great, take that and put it over here and do another action to it. If you've heard about like the Core M Duo processor, that's essentially a processor that has lots of places to do computation. So it can move things around and do computation in parallel. And it can convert things, right? So we'll talk a little bit about what a 32-bit versus a 64-bit integer is and why that would matter. But one thing a computer can say is essentially read this language as though the words are 32-bits long, or read it as though they're 64 bits long. And you can see that this works well in one direction and poorly in another, right? If something is written to be interpreted by 64-bit processors that operate on 64 bits of data at a time, doing those same operations on a 32-bit machine is going to be dramatically slower, right? This is why emulation works, essentially, right? Is that a faster machine can do all of these same operations, and because it has a bigger pipeline to do them, it can essentially mimic another machine. This is called, if you talk to people in computer science terms, Turing compatibility, right? That whole page I showed you is everything a computer knows how to do. And the questions from there in computer hardware design are how fast can it do them, and in what order is it going to do them? Is it going to do them all at once, or is it going to do them sequentially? And if you think about this in human terms, right, the way we work with data, it's a mess, right? We are not computers. There's no memory bank. There's no parallel processing. If I try to read every line of Ulysses at once, I probably just get the same thing out of it as I would reading it from beginning to end. If I try to read every line of Shakespeare at once, it's just soup, right? If a computer does that, if you ask it to find the word thou, it can happily read every line of the text at once, because the text as the computer knows it is just a symbol of a set of voltages. So it's just looking for the reoccurrence of a pattern in many places. And you can divide that grid of voltages that represents Hamlet up any way you want, and look in those grids, in those spaces, all at the same time, one after another, make your selection, right? All existing computers have this base level of compatibility. They all do the same things, and the questions are whether the data you're giving them is encoded in a way that they know how to read it, whether you've given them appropriate instructions. As we get into the early 20th century, the change that we make is not from repeating a sequence of operations, but towards programmability. So being able to interactively change the flow of a program or give a system new instructions on the fly. The first real breakthrough in this is in '37, George Stibitz builds the Model K calculator. It was named for the kitchen table that he built it on. And it was the first computer to use binary circuits, what we would think of as modern electrical hardware, to do arithmetic. And it led to the building of something called the complex number calculator at Bell Labs. Turing's paper is just paper, right? It's purely a philosophical or logical construct. Stibitz is one of the first people to start realizing some of those concepts in hardware. Some of you have probably heard of ENIAC, right? Widely considered the first general purpose electronic computer. So you could go to ENIAC and say, ENIAC, here's a series of instructions, right? And those instructions are exciting things like charge your vacuum tubes in this order, and then add to those charged vacuum tubes this different set of charged vacuum tubes, right? If you do that enough times, though, you can like send a rocket on a particular trajectory. ENIAC is followed by a series of computers, EDSAC, the ABC, the Z3, all of which are programmable. The first one to really break through is the Colossus, built in the UK by Tommy Flowers. And this computer has the virtue of being fully programmable, right? So it doesn't just have a series of instructions or mathematical operations it knows how to carry out. You can explain to it how to carry out an operation, right? So you can give it a set of instructions for performing a function and then give it data and have it perform that function on the data. Most of what's happening right now is math, right? But I hope it's possible to see or easy to see how math can stand in for anything, right? If you assign this pattern of, charged, charged, not charged to the letter A, all of a sudden you have a computer that can do word processing, right? So here's what these glorious things look like. That's the Model K, or a replica of it. There's someone working on the complex number calculator. There's ENIAC with Betty Jennings and Francis Billis, who were the first programmers for it. Here's Colossus, Dorothy Dubuisson and Elsie Booker, who actually just did an oral history with the Computer Museum, talking about early computer programming. Colossus is being reconstructed right now over in London. And these computers were interesting in that the programs were all independent, right? So Colossus was essentially a blank rack of vacuum tubes, and if you knew how they were connected, you could essentially push on them in certain ways and have a predictable output at the end of them. We didn't yet have what we would think of as an operating system, right, that provides a standard set of operations that you can call abstractly. So if you're programming now, you just say, operating system, add these two numbers. If you're programming that on ENIAC or Colossus, you have to say, here's addition, right? And you have to do everything from first principles. So the first real development in computer programmability is an abstraction layer, right? The notion of an operating system that generically understands things like addition and subtraction or printing to the screen. there's a preservation implication here about understanding the usage environment, right? The data on a particular piece of media may be completely intact, the media may be readable, but if you don't have the operating environment that it's intended for, you're still a long way from having preserved that thing. So understanding what systems people had and how they were used is often a really critical component. And finding that knowledge is often an oral history project as much as it's any sort of like technical research project. So before we move on, I'm just curious to, as a trivia test, anyone know who the first computer programmer was, or arguably? Yeah, Ada Lovelace. She wrote this incredible paper. She corresponded with Babbage, wrote this incredible paper essentially saying to him Babbage's world was all math all the time. A great anecdote about him shouting at his friend late at night as they were making up mathematical tables. I wish these could be calculated by steam, just to say that automated. Lovelace wrote to Babbage back and forth. They had a long correspondence on all sorts of subjects, but she essentially gave us one of the first accounts of computer programming, essentially saying, we've been thinking of this as adding and dividing and manipulating numbers, but a number is just a symbol, right? It stands in for some abstract quantity. A number could represent a word, it could represent an idea, it could represent an image, and really what you have, Babbage, is a symbol manipulating machine. You have a machine for performing logical operations, and if you have that, you can do anything, right? You can print poetry, you can describe the contour of a flower petal. You can also ask it a series of questions and a series of ifs and thens, right? And so Ada Lovelace really emerges as the first person who gets it, right? That computers are symbol manipulating machines, not just sort of mathematical calculators. So here's my bonus round. Why am I showing you this? Let me back up one. What is this? It's an organ, right? How does an organ work? Anyone want to offer it?
Forces air through pipes to create
Yeah.
musical tones.
You have keys and pedals, and as you press them, it opens and closes different stops. Why would this possibly be of interest to us?
Because you can set and change those stops.
Set and change those stops, right? So you can take the logical instrument.
And you can program it.
Yeah.
Based on the stops.
Right. You can also take something like this. What organ can I play this on? Does it need a specific organ? Any organ? Right? Why not? I can make choices about how fast or slow I'm going to play it. I can choose which stops I'm going to play it on. Essentially, what you are doing, or what we are thinking about doing right now, is emulation, right? We're taking an instruction set and we're saying, given a sufficiently powerful organ and a sufficiently capable player, I can take this instruction set and I can cause it to occur in different operating environments, right? And you can see this as a manual, right? A right and left hand and a pedal, right? So I couldn't emulate this on a piano, right? I would be missing the pedal, or I would be a very clever pianist. I would need an organ and an organist of sufficient power, right? If I personally tried to emulate this, we'd be in some real trouble down here in the fourth stave. I think I could get us through the first line comfortably, maybe, but by the middle of this, we would find out that the processor lacks sufficient bandwidth, right? There would be certain organs that might not have the whole range. There might be notes too high or notes too low. There might be certain exemplars of this performance that could only be done on a certain organ, right? So the recording we're listening to now, if you're a real organ nerd, you might be really excited that it's being played on that organ in that cathedral, and only that organ in that cathedral will do. If you're just generally interested in listening to Bach, There are a lot of organs available to you, right? So everything that happens in emulating a computer program is basically happening here, right? Every time a symphony orchestra sits down to play, it is going through the process of emulation. Anyone follow like classical music and historic performance practice debates? So, is it okay to play Mozart on contemporary symphonic instruments? Yeah, right. Different use cases. If your goal in hearing Mozart is to hear all of those pitches in order, modern symphony may do. If your goal is to hear Mozart as Mozart heard it, period instruments may be the only acceptable choice, right? Both perfectly valid, right? Both of those activities, historic performance and modern concert hall performances, serve to keep Mozart, the music, preserved and keep it available. But if you're concerned with one approach to it, one of them can fail at the same time it's succeeding in another preservation purpose. All right. Good. We're fine on time. Let me pause for a second. Does that help? Are those ways of thinking about emulation and computing useful to you? Somewhat? Okay. How about migration? We haven't explicitly talked about it, but have we implicitly talked about it? Yeah, translating a language, right? Going from Greek to Cypriot or Greek to English, right? Everything you do in digital preservation is, and the reason to understand the computers are symbol manipulating machines or machines for repeating logical operations, is to recognize that most of the solutions happen using technology, but you're executing something that has a larger life, right? Preservation, the question of emulation, migration, choosing a particular technology, those are things that happen in every kind of preservation. And the questions you need to solve are which approaches, which tools are appropriate to my domain and the people that I'm keeping this material available to serve. So I want to take you, we've gone antiquity, the 19th century, the early 20th century, and now in the next 10 or 15 minutes I want to bring us up to the present, and then we're going to get into sort of our pivot exercise that brings us into the afternoon, where we really start talking about how digital preservation is enacted in a contemporary setting. So the predecessor technologies to all the work you're going to do today sort of start with the mainframe. It's named for its physical characteristics. It was large and it had a frame, and you hung parts on the frame. You'll hear occasional crusty old programmers talk about big iron, and you probably are still interacting with some of these mainframe systems. If you've gotten, like from your bank, a sort of all caps statement, or you've gone to, say, Penn Station or Boston South and you've seen like the train listings, right, and wondered why they can't just print New York Penn Station and why it's NY Penn. There's probably still a mainframe ticking away there that specifically knows how to talk to that large illuminated board that hangs in the middle of Boston South Station. I know I see it every time I'm at New York Penn, as I was coming up here. There's the large reader board in the middle, and it has this, what I consider now hilarious as a digital preservation problem, little extra display below it, and it says, SEC means Secaucus, and there's one other, I think it's ARP or AIR means Newark Airport, right? Because the display says something like Trenton Ni Cor Sec, right? And if you're an NJ transit rider, you're like, oh, that's the Northeast Corridor line on Trenton and it's stopping at Secaucus, right? If you are any of the other poor unfortunate souls who have blundered into Penn Station and you're trying to get to the airport knowing that where it says like Ewer or Air or something, right? And they've clearly fudged this in, right? Because they can't change what the mainframe says to the display. So they've added this little line of text explaining the cryptic code that is appearing up there. The goal of a mainframe is to be reliable for transactional processing. It's worth pausing here to say, if you've heard the term floating point operation, are there any video game players? I mean, like, serious video game players, like, you have opinions about NVIDIA chipsets and a couple? Okay, good, right? So, video game graphics are floating point intensive. It means that they do lots of math to a large number of decimal places very quickly. So, if you want to, like, draw the shadow on a polygon, that's a floating point intensive operation, right? You're doing complex math on the fly. Transactional processing is different. Transactional processing is inventory management. So it's creating and moving data from register to register, right? Remember we talked about bit shifts and copy actions. So a system that can do math to a very high degree of precision very rapidly can't necessarily move data around quickly. Mainframes are built for data moving. They're card catalog type devices. And that's one of the reasons they still persist, right, is that if your goal is to just make sure that every train is in its slot or every bank transaction is filed, you need to do rapid, reliable transaction processing. And the systems that did it well 10 years ago still do it pretty well today. Whereas floating point calculations, each new sort of generation of chip architecture gives you even more precision at even greater speed. So disk read writes, calling the operating system, moving data place to place, that's really where mainframes specialize. So updating something for inventory control, doing financial transactions. Supercomputers, right, are sort of the other variety, right, where you're trying to finely calculate. If you want to do climate and atmospheric modeling, you need floating point operations, right? You don't need transactions. There are some mainframes, right? So the classic sort of reels of tape, but also, you know, there are plenty of kind of elegant new systems that still do this heavy transactional processing. Mainframes, sort of from ENIAC into the 70s, get supplanted in the 70s and 80s by the mini computer. And this is, again, an ill-defined class of machines. They are mini computers because they're smaller than mainframes. They're still quite large. New York Times had a consensus definition, costs less than $25,000. It has some way to get data in and out of it, like a teleprinter. Has at least 4,000 words of memory. That's not enough to probably send a tweet. And capable of running programs in a higher level language like Fortran or BASIC. So it has a programmable operating system. It's sort of obsolete terminology, but it's basically all the things that a contemporary server does, right? So lots of devices can talk to it. It can move data around pretty quickly. And it's relatively affordable, right? So they come in all sorts of shapes and sizes, but this was the beginning of what we would think of as the modern computing era, where you have a device and you have languages you can use to talk to that device, right? So a mainframe, you might only be able to talk to the mainframe in its own language. A mini computer, if you're a Fortran programmer or a COBOL programmer, you can work on all sorts of different manufacturers' devices. And eventually you get the emergence of things like Unix, right, where there's an operating system that has certain calls. And so the level of abstraction from this person knows how to make this machine work, to this person knows a language that this machine understands, to these machines, we don't really know much about them except that they all have this operating system, and so anyone can talk to them. It is really what happens during the last part of the 20th century. Essentially, everything we have around us now fits the basic idea of a mini computer, right? Fairly inexpensive, has some way to talk to it, has some higher level languages and operating systems that it understands. I see Mac OS 10 something. I've seen some iOS devices. I don't see a single Windows computer. All right, good. So a couple of them are around, right? Some of us, whether we intend to or not, are running Unix, at least under the hood of Mac OS, right? They all perform the same basic function, right? They have an abstraction layer between this processor, so you don't have to deal with thinking like, where are the logic gates in this computer and how are they arranged and how do I send data to them? You just have to know C++ or Java or whatever your language might be. The one sort of giant piece of technology we have not talked about is the internet. And rather than sort of bore you with explaining the internet, I want to actually build one. So I think we'll start by playing the game of network. So we talked about mini computers being essentially like what we think of as the server. A server is a network-connected device that performs store and compute functions, so it can keep data and it can do things to data. Often both, right? And it's worth always remembering that server can mean the actual piece of hardware, or it can be the service, right? Sorry, went the wrong way. So server, the thing, right, is an actual device, usually has a lot of network connectivity, so many things can talk to it at once. It could be the laptop I'm working on. It could be a supercomputer in a data center. The point of a server is just that it has multiple users, right, and can handle many transactions. We also talk about server, the software, right? So servers, as we experience them, tend to be things like the Apache web server or a streaming media server, right? That is a service we interact with. Apache, I choose just because it's the most widely used server. And it's worth sort of knowing that it was developed in the mid-90s, right? This is I look at this in two ways. One, gosh, it's radically new, right? Like 20 years ago, everything we do normally today was fantasy. On the other hand, 20 years is a pretty good run, right? So the fact that we're still using this 20-year-old technology in terms of our risk management job in preservation should be a key or a sign to us, right? That obsolescence and catastrophe is not the inevitable outcome of digital, that digital is something that has a kind of managed process. A couple principles we always look for. Objects are kept on storage media. We can keep objects online, so we can talk to them directly. We can keep them nearline, or we can keep them offline. Ideally, we're going to make a decision that gets us the most copies in the most places, but cost is going to be a factor. Quantity is going to be a factor, right? If you're dealing with preserving 4K motion picture films, we will probably end up with fewer copies than if you're preserving image files. Expertise, right? Who's going to manage these things? Do they require a lot of human intervention, or is this automated? Who can you work with if you're trying to get geographic distribution? Who's going to provide services for you? But in general, we're trying to get more than one copy in more than one place, right? And we'll make decisions from that based on sort of restrictions. So to give a sense of how this works and what the risks are, I want to do a little simulation, right? Where we'll play the game of packet switching network, right? So the internet works in an interesting way, right, where it doesn't have direct known point-to-point communication, right? So if you send something out over the internet, you sort of know the address it's going to, you know how where it's going to arrive. You don't know how it's going to get there, and it is in fact completely unknown until it starts to travel. And the idea of a packet switching network is that you have many connections so that you're never dependent on any one of them to be able to send something reliably, right? A direct transmission network is faster and simpler, but if the direct line of transmission breaks for some reason, you're just stuck. You can't send data. So we're going to simulate that. I'm going to pass around cards, and I want you to write two things on this card. One is your real name, and the other is some fake name, just some identifier we can call you by that is not your real name. Preferably an identifier in a language I can read and pronounce, which basically limits us to English. Just give yourself a fake name. So I might write Jake, and I might write below it Bob, right? Perfectly acceptable. I'm also going to pass around a set of cards, and they're going to have kind of cryptic labels on them, like CM1, CM2. And we're going to pass these cards around at random at a steady rate. And I'm going to play the role of the leader in this game, and I'm going to say things like, Chris, CC2. And if you are Chris, you're going to look at the card in your hand, and if it says CC2 on it, you're going to take some action. If you're not Chris, and you have a card that says CC2 on it, you're going to give it to someone else, right? So if you have the card, but your name was not called, you pass it. If your name was called, start counting, right? So we'll do this. So if I'm Chris, I'm going to say, like, nope, it's 1 pass, 2 passes, 3 passes, 4 passes. Aha, now I have the card, and then say, I've got it. And you'll read a definition that's keyed to it. And then periodically, I'm going to mess with things as people mess with the internet. So here are the things we'll be reading. Don't worry, the internet has no front or back. It's just a series of tubes through which cats are transmitted. If Rebecca is touching you on the shoulder, don't pass any cards. And if Rebecca gives you instructions of some kind, just try to do your best.
Just take this as a cue for the rest of the residents.
Yeah, that's right. Yeah, in this game, as in life, when Rebecca tells you to do something, please make every effort to follow those instructions. So pass once. Just make sure you have a different card in your hand than
I have 2 hit cards.
yeah, send one away. Pass again.
Here you go.
Oh, yeah.
Now, Leslie, can you read CM1? Oh, wait, don't. Do you have CM1?
Oh, no, I don't.
All right, so let's pass once.
Everyone?
Yep, everyone, just anywhere. And pass twice. And Leslie, just give us a shout when you get that card in your hand. Pass 3 times. Pass 4 times. Pass 5 times. Oh, you got it?
CM1?
CM1. Read it out for us.
A robust computing and networking infrastructure.
Yes, necessary for content maintenance according to the American Library Association's Association of Library Collections and Technical Services definition of digital preservation. A robust computing and networking infrastructure. So, you didn't know where CM1 was when we started this whole exercise. Some of you probably didn't know who Leslie was when we started this whole exercise. It's okay. I barely know who Leslie is, right? 5 turns of the internet, we got it to her. So let's try another one. Karen, give us a shout when you have card CM2. Let's pass once. Let's pass twice.
Sure.
Let's pass 3 times. Let's pass 4 times. Let's pass 5 times. Let's pass 6 times. And 7. And 8.
Is someone allowed to have 2 cards?
You might end up with 2 cards at some point. Just try to get them out of your hands. Let's do another pass. 9. 10. 11. 12. All right, so we've got a problem, right? Something is pinging around the network and it hasn't found its location. Who has card CM2? Okay, and where is Karen?
Here.
All right, let's pass 13,
Where was CM2?
14,
I didn't pass.
15, 16.
Ah, got it.
Got it? All right, so here we know two things, right? Just randomly, a packet switching network eventually can probably get something to the right place. But the odds are pretty bad as the network gets bigger and bigger and bigger. With pretty minimal information, right? Requester and resource, we were able to connect that in 4 passes after nothing happening for 12. This is basically what happens when we do directory lookup, right? You call into your local ISP and you say, hey, me, IP number, et cetera, et cetera, et cetera, I want this resource. And it says, where the heck is that resource? Right? And the network connects itself. You didn't make any plans, intervening people, right, and CM2 passed through. You didn't collude before the session began.
I do note that some nodes on this network are more active and more connected than others. So Karen only has 3 possible connections that she can
That's
make.
correct.
Whereas, I'm sorry, I don't know your name. Katrina and
Adam.
Adam both have up to 8.
Yeah.
So.
And this is additionally a factor of the internet. First, read out CM2 for us.
CM2, synchronization and storage of files at multiple sites.
All right. A good segue is talking about network connectivity. So, Rebecca, do me a favor for this next one. Shut down a couple nodes in the center of the network. And what we're going to do is try to get CM5 to Andrea. Let's pass once. Let's pass twice. Let's pass 3 times. Let's pass 4 times.
Keep passing. Oh, keep passing.
What do you think?
Yeah, we're CM5 to Andrea. This is 5 times. 6 times. 7 times. 8 times. 9. 10.
Which is Andrea?
Back there.
11.
Wait, you didn't say pass.
Oh, my.
Oh yeah, go. So this will be 11, 12, and 13.
I have it.
All right, read it out for us.
Creation and testing of disaster prevention and recovery plans.
Yeah, right. What do you do if right in the middle of the network there's a gaping black hole, right? And things stop passing data around. Took a lot longer. Does anyone remember if you had CM5 when we began that?
I think it might have been me, actually.
So that's really interesting, right? With a couple network nodes shut down, it's really difficult for you to get that data out. CC3, let's get that over to Rachel.
And you guys need to keep shuffling.
Yeah,
Don't pass anything. Just keep putting things in order.
Keep busy. 1, 2, 3, 4. Let's do one more here. 5, 6. Can you put those in order for me? Yeah, thank you. 7, Rachel for CC3. 8. 9. 10. 11.
Who else?
Me, but
All right, so pause for a
Rachel
moment.
can't accept it until she's done.
Rachel, can you please identify yourself?
Yes.
Yes. Why can't you get CC3? Yeah, so our internet is experiencing a direct denial of service attack. Right? Rachel has been given so much to do that she can't actually accept any data right now. Nor can she pass it. What card do you have?
C13.
Right, so if we did CI, it's my bad handwriting. If we wanted to get that data out, we'd also be stuck, right? She has 50, actually you have 54 cards to put in order. Right, this happened recently in the Library of Congress. You probably heard this happening in lots of other places, right? Essentially just a swarm of requests hits a particular point in the network. And pretty soon, we saw it happen here, right? It started to get very confusing about how we should route anything. So this is the elect's definition of digital preservation. It's a document that still is fairly useful. It was developed out of the preservation section of the American Library Association, but in consultation with professional societies in computing and technology, as well as kind of peer groups in archives and museums. The reason I introduce it to you is partly because you have here 16 different areas of preservation you could work in, and it's worth thinking at your institution whether any of these things are relevant in the next year, right? Probably 12 of them are going to go out the window right away when you think, can I do anything about this in the next 12 months? But also to recognize that in each one of these things, you could have progressive goals, right? So you could think about something like, say, detailed quality control of processes. And you might say, gee, we have dozens of processes, but here are 3 that we can make progress on this year. And that progress is still progress. And so this is yet another framework, a nice way of breaking down preservation into potential projects you can do, and also thinking about what would look like nothing, something, good progress, excellent progress, and in some cases, progress I don't need to worry about at my institution. And recognizing that there are ways to sort of structure and deal with the work you're doing is really the key to success in any kind of preservation. So we've done it. We've gone from Bronze Age mark making up to the modern internet. And I hope you see some continuity, right, that there are some fundamental questions that apply to all of these things, and that it's possible to break them down into manageable chunks that we can actually take preservation action on. With that said, I think time for self-preservation. Let's
Whenever America gets a new president and a new vice president, a team of government workers in the General Services Administration is responsible for taking down photos of the outgoing president and vice president and putting up photos of the incoming team. While the rest of the country is digesting the election results and slowing down for the holidays, this team is working overtime.